Here we are at the Australian New Zealand Society of Nuclear Medicine meeting in Melbourne, and we're privileged to be talking to Dr. Cherry, and he's been here talking about some of the new developments with particularly PETMR, which has come in many varieties and shapes and sizes. I think it's still, would you agree, in a developmental phase at the moment?
It is, yes.
So, so perhaps we can talk a little bit about PETMR and the new technologies and the new detectors that may or may not happen, and the things that may or may not happen with that area, and also what applications, perhaps might come along. So perhaps we could start, if you could tell our listeners a little bit about where you work and what you do.
Yes, so I'm a professor at the University of California in Davis in the Department of Biomedical Engineering and Radiology, and the interest in my lab are developing new imaging technologies, trying to improve spatial resolution, improve sensitivity. And we're very interested in combinations of modalities, trying to take advantage of complementary strengths, and that's how we got interested in PETMR in the first place, some 15 years or so ago now.
Right. And I mean, one of the things with PETMR, originally it was thought that MR might be useful in terms of using the magnetic field to improve the resolution of PET, because that's if you apply a magnet, that stops the positron moving a certain distance. That's where it began, but that's probably not even where it's finishing or where it's going. So if you could perhaps briefly go through, what's happened with it so far.
Yes, sure, and certainly that was some of the initial motivation. I think people thought that strong magnetic fields might be a good way to reduce the positron range effect in PET and improve spatial resolution. And in the mid-1990s, several laboratories were trying various approaches towards accomplishing this. And then I think people started to realize that the potential of PETMR was far more than that, that MR was much more than a strong magnet, and also much more than just structural imaging as well. There is just such a wealth of information that you can obtain from MR, and much of it's very complementary with the kinds of things that we can do with PET as well. And so that really refocused everybody's efforts on really trying to develop very high-performance imaging systems. And a lot of this started in the preclinical area. It was a time when there was a lot of development of preclinical imaging technology. The pharmaceutical industry got very interested in these technologies. And in the United States, National Institutes of Health started funding quite a lot of this instrumentation development. And of course, it was also around the time that the combination of PET and CT came along as well. So that was an exciting time.
Right, and so part of the challenges was, of course, is if you've got a magnet, it's going to muck up the photomultiplier tubes that are used in PET imaging, and so people started by using optical guides to move the bits out, but that's not a great solution, is it? No,
absolutely not. So it was at the time it seemed to be the only solution, and people used light guides, optical fibers, to extract the light from the scintillation crystals out of the magnet. And while you could build proof of concept systems this way, you really couldn't build high performance PET scanners. You just couldn't get many detectors into the magnet before the bulk of the light guides or the fiber optics would overwhelm you. So the big step forward was really the point at which avalanche photodiode light sensors became robust enough to be used in PET. Because these are silicon-based detectors, they're very compact, they're very insensitive to magnetic fields, and that really provided a solution which allowed us to build much higher performance PET scanners inside of magnets. And so that opened up a whole lot of development, which has ended now with what we're seeing in the commercial world, some of the first fully integrated PETMRs for human imaging now.
Right. So these machines, so Siemens make one, and are there anybody else with avalanche photodiodes making them?
I don't know what some of the other companies are doing. I know there are R&D efforts in all the major companies to develop fully integrated systems. Avalanche photodiodes are a good solution now, but they may not be the ultimate solution.
Why?
Why? Because their timing performance generally isn't very good, and there's been quite a move in PET imaging the last few years to move towards time-of-flight imaging, because you get a signal-to-noise improvement by doing that. and so you can't really do time of flight with avalanche photodiodes because their timing is not good enough. So what is on the horizon are these photodetectors called silicon photomultipliers. These, again, are solid-state devices. They're actually based on a large array of individual little avalanche photodiodes, but the critical thing is they're operated in so-called Geiger mode, which is a mode where you bias above the breakdown voltage, and because you do that, you get really good timing from them. So now you've got the best of both worlds. You've got a compact silicon detector, so you don't need to take up a lot of space in the magnet. It's field insensitive, so you don't have that problem, plus you have the timing as well. So I think ultimately my best guess would be that we're going to see that technology in PETMR scanners in the not-too-distant future. And we're already seeing it in prototype systems out of academic labs. That's already happened.
Right. So PETMR scanners, we know, these are new technologies, so they're going to be mega expensive. All right? So given that they're mega expensive, why would you want one?
That's a really good question, and a lot of people are asking that question. I think there are certainly hints of some of the applications out there. I think in the field of pediatrics, the fact that we can do perhaps really low dose PET, and now with MR we don't have the radiation dose associated with CT. I think that's an attractive area. I think the ability to get very high quality PETMR data, and by high quality I mean that they're perfectly registered spatially, is potentially very valuable clinically. But I think the cost effectiveness is a real question, and it's something we have to see. I mean, I think in many countries in the world there's huge concern about the spiraling cost of healthcare, and this is definitely not an inexpensive solution. So while it's a very powerful technology, and as a research technology, I think it's fantastic and will clearly have a role. Its ultimate clinical role will really depend on showing that it's cost effective, that the information that it provides is saving money somehow, either by preventing unnecessary surgeries or by preventing people staying on expensive drugs for too long. Those are the kinds of areas where you could save a lot of money potentially and justify the cost. Right,
and it's really got to be doing something that we can't do with to justify the cost. It's got to be something we can't do with PET-CT.
That's right.
So you said about the image registration. How could we use that in special ways? Perhaps with motion correction and things like that might be a big advantage with the PET, for example?
Yes, so the fact that you can track the motion very nicely with MR using navigator echoes, so the potential, even though you're integrating the PET image over a fairly long period of time, to actually correct motion during that time, so that could get us better spatial resolution, allow us to see smaller lesions. That's certainly true. And then the other question is whether some of the other MR techniques that go beyond structure and the combination of those with PET will provide important clinical information. That's yet to be seen.
Right. Well, PET can provide information. Let's say you had a PET tracer that's going to give you good biochemical information about how the biochemistry of something's happening. But we don't know whether the accumulation of that biochemical is due to the chemical function or whether it's perhaps due to the blood flow. Perhaps you could use the MR to tell you about the blood flow to the area, tell you about how those sorts of things happen. So that we can, by tightly integrating those two, we can tell more about how that function works. And again, you said in early biochemical development, that's an area where it could really help, because at the moment we're doing amyloid work, we're doing work that may have a massive impact in medicine in general in terms of working out what drugs are going to treat diseases. Maybe we won't use it in the clinical place, but maybe we can use it to figure out what drugs are going to be used to treat different diseases and whether they work or not and how they work in the body.
That's right. I completely agree, and I think there are lots of ideas like this out there, and I think that the big thing now is to collect the data to support whether these ideas are really going to have a clinical impact. And so I think that's why it's so great to see industry now being very committed to PETMR, to see systems going out into the field in the hands of many top researchers across the world. And we're going to get lots of data in the next 2 to 3 years, which will start to answer some of these questions, I think.
It's come at just at the right time, because now we're starting to do with very advanced studies of how proteins work in the body. We're actually getting to the point where we can actually do personalised medicine, where we can actually do treatments, where we can actually work out how things work. And coincidentally, we've just come along with the right kind of imaging in order to do that. it's funny how some things come together all at the same time.
That's right, and I think the future of molecular imaging is really strongly tied to the future of personalized medicine. And I think it's going to be very interesting to see how healthcare evolves in the next 10 to 20 years, whether we do develop better approaches for personalized medicine, and the role that molecular imaging will hopefully play in that, which is to help select the right patient for the right drug.
Okay. So where do you think we're going to go next? Are we going to go to PETMR? Are we going to go to? Are we going to have some combination of optical imaging, perhaps with what we're doing? Perhaps. What do you think's the next step?
Well, certainly people are exploring just about every combination that's possible, and I think in each case there will be certain niche applications. PETMR certainly will have a lot of the same advantages as PETMR does. It will open up some other radionuclides that can be used. Again, it's going to be pretty expensive though, and so you lose some of the cost advantage that SPECT has over PET if you combine it with MR.
But maybe it's an advantage in animals because you can get very high resolution with SPECT, much better than PET.
Oh yeah. So if we're coming back to the preclinical area, then I think it's a different matter, and so there definitely there's a role. And also in the preclinical area, optical imaging, of course, is the most widely used modality, and so certainly people are exploring combinations of optical with CT and optical with MR, and actually having the structural information can be very helpful in guiding the reconstruction process for fluorescence or bioluminescence, which is a very ill-posed problem, a very difficult problem. The challenge again, though, is a cost thing. So one of the reasons that optical imaging is so widely used is because it's very simple and it's fairly inexpensive. And now, if we add MR or CT to it, it increases the complexity. It takes it out of the range of a technology that can be used in individual labs. So now you're talking about core facilities again. And so it's not clear whether it's best to keep things simple, but with limitations in the preclinical world, or to move to very sophisticated devices like PETMR, SPECT-MR, that potentially are more quantitative and can be used for a wide range of applications, but are very expensive, and then you have to have core facilities that will support that. So I think all of this is still evolving.
So basically what you've said, there's far more questions that you've posed than answers.
Yes.
Is that a fair question?
I think that's so. I think certainly in the area of PETMR it's still so wide open because this is, for most people, such a new technology. I mean, we've been exploring it for many years, but it's only in the very recent past that commercial systems have become available, and so this technology is finally getting into the hands of people across the world, and it's going to be very interesting to see what they do with it.
Okay. So how can people find out more information?
About what?
About these new technology, about what you do, or about PETMR. Where would you start looking?
It depends at what level you want to look. I mean, there's a lot of information out in the literature. There are conferences that specialize in this area. I mean, the World Molecular Imaging Congress is a great conference because it spans all the different specialties. The instrumentation, the chemistry, the biology, the clinical applications. And for the techies, there's the IEEE Medical Imaging Conference, which is where we get down to the nitty-gritty details of all the technologies. But then there's also a lot of information out on the web, of course. A lot of the companies that produce these detectors have information out there, and a lot of the academic groups now, provide a lot of information on their website, and certainly we try and do that in our lab.
Okay, so perhaps I can give a link back to your lab.
That would be terrific. Yes, thank you.
And we'll pop that on for the podcast.
Yes, that would be great.
Fantastic. Well, thank you very much for speaking to us.
It's been my pleasure.
Okay.
Thank you.
Thank you. Good.